Hello, it's Scott Manley here, and today I want to do an extra episode of Going Nuclear, where we talk about why the reactor number 4 at Chernobyl exploded in 1986. Now, obviously the catalyst for this is the TV show Chernobyl on HBO and Sky, and I'm going to say right away, I love the show. It's fantastic. I've watched it all the way through, and I think some of the details it goes into is great. It's not perfectly accurate in every way, but I do think that the courtroom scene in the final episode is an exceptionally good explanation of what happens for the layperson. However, I do think that they glossed over a number of important mechanisms, which I would love to talk about. So, I mean, the TV show is still superior to practically any documentary I've seen on the subject. So, you know, there are some really terrible documentaries out there. I would watch this TV show before those. I'm also not going to talk about the people involved. I'm not going to name names. I'm not going to talk about the aftermath, which is also full of amazing stories of, human heroism and tragedy, because of course the TV show does this exceptionally well. So let's try to get down into the weeds on how nuclear reactors operate. Many of the details I'm going to talk about here have already been discussed in my series Going Nuclear, so that's a good place to be, but if you haven't watched that, it'll be suitable for everyone. A nuclear reactor works as a self-sustaining chain reaction where atoms of uranium or plutonium are split into smaller, lighter atoms, and as they do that, it releases energy. This is called fission. Now, as the atoms split, they also spit out high energy neutrons, which bounce around inside the core, and some of them end up hitting other uranium or plutonium atoms and make them split. Now, reactors are balanced so that the average of one neutron per reaction goes on to trigger another reaction. If the average is slightly higher, then the reaction rate will actually increase, and if it's slightly lower, the reaction rate will decrease over time. Since each fission produces 2 to 3 high energy neutrons, they need to get rid of the excess neutrons somehow. There are 3 things that can happen to these. Firstly, they can go on to trigger another reaction. They could escape the core completely and be lost, or they could be lost by being absorbed by another type of atom that doesn't undergo fission. Reactor designs include materials inside them that are designed to absorb the extra neutrons. These are materials like boron or cadmium so that they can keep the reaction rate constant. Some of these absorbers are in the form of movable control rods that can be moved in and out of the core to dynamically change the neutron absorption rate and keep the amount of excess neutrons constant. The nuclear fuel used in the reactor at Chernobyl is uranium. Naturally occurring uranium is made of 2 primary isotopes. There's uranium-238, which is the most common, and instead of splitting when hit with neutrons, it tends to absorb them instead. Uranium-235 is much rarer, but when it's hit by uranium, that's the one that splits and releases the energy. So for naturally occurring uranium, only about 0.7% is the fissile uranium-235. However, in the first nuclear bomb dropped, the little boy, its uranium was enriched to something like 80% uranium-235. Because of complex nuclear quantum physics, which I'm going to completely gloss over, the chances of a neutron being absorbed or triggering fission changes with the energy of the neutrons. In uranium-235, the chance of a neutron causing fission is about 1,000 times larger for low energy neutrons as it is for high energy neutrons. The neutrons that come out of each fission event are very high energy. They are moving at a good fraction of the speed of light. So reactors are designed that they can slow these neutrons down closer to the speed of sound, and they do this by having the neutrons bounce around off the nuclei of atoms, and every time they bounce, they slow down a bit. The best atoms for this job are the ones which rarely absorb neutrons and which are very light so that each bounce transfers as much energy as possible. Most commonly we will see reactors using either carbon in the form of graphite or hydrogen and oxygen in the form of water. These materials which slow neutrons down are called moderators, and they make it possible to run a nuclear reactor without spending a lot of time and effort enriching your fuel to weapons grade levels. It's worth pointing out that regular hydrogen still has a reasonable chance of absorbing neutrons, which does offset its utility as a moderator, but it does work if the fuel enrichment is high enough. Deuterium has a much lower chance of doing this, which is why heavy water is used in some reactor designs. At Chernobyl, the reactors were the RBMK design, which is a Russian acronym for Reactor Bolshoi Moshchenosti Kanalny, which I think is roughly translated as high power channel type reactor. The channels are a series of pipes that run vertically through the core of the reactor, which carry cooling water, and they contain things like fuel rods, control rods, neutron sources, instrumentation, depending upon the configuration of the reactor. While many water-cooled reactors use water as a moderator, in the RBMK reactors the neutron moderator is primarily graphite blocks that are placed around the channels. This was a design decision which made it possible for the reactor to sustain a reaction using unenriched natural uranium as a fuel without resorting to heavy water as a coolant, and this made it a very cost-effective design. A set of electrical pumps would drive the water through the core. The pressurized water entered from the bottom of the core, absorbs heat from the reaction, and after leaving the core, the steam is then separated and used to drive the turbines. And so we come to the test. That was a series of procedures being performed on the night of the accident. In the event of an emergency, the reactor would be shut down, but the cooling process had to continue. The reactor continues to produce heat after the reaction stops because the split atoms are radioactive on their own, and they're slowly decaying and releasing energy, and that meant that you couldn't immediately turn off the cooling water to the reactor. So those pumps had to keep operating, and to make sure this happened, there were diesel generators that could start up and provide power to the pumps in an emergency. However, those generators would take about a minute or so to come up to speed, so another energy source was needed for that first critical minute. And that energy was supposed to come from the already spinning turbines and generators. As the steam generation stopped, the turbines would begin to spin down, but they would still have kinetic energy, and so they could continue to generate electrical power as they converted their kinetic energy into electricity, and that would keep the pumps running for long enough that the generators could kick in. This had never been successfully demonstrated for Reactor 4 at Chernobyl. The voltage regulators had always let the power drop off too quickly. So this test was supposed to be the one where they finally showed that this safety system could work. The reactor was being brought offline for maintenance anyway, so it was scheduled for the time when they were shutting it down. However, that day the power grid had needed more energy than expected. That meant that Reactor 4 wasn't allowed to be taken offline when planned, and instead the reactor continued operating at a relatively high power level until late into the evening. Now remember, I explained that the balance of neutrons being absorbed is important, and how neutron absorbing isotopes are used to control this. One of the most critical fission products that builds up in the core is Xenon-135, and it is exceptionally good at absorbing neutrons that would otherwise sustain the reaction. But Xenon-135 doesn't appear instantly. About 95% of it comes from iodine-135, which has a half-life of about 6.5 hours. So if a reactor has been operating, the xenon from the reactions only appears about 6.5 hours later. As a reactor operates, the amount of Xenon-135 in the core grows until it reaches an equilibrium. And the extra neutron absorption from this means that less neutron absorption is needed from the control rods. In nuclear engineering, Xenon-135 is referred to as a neutron poison because of its ability to kill the reaction by robbing it of the neutrons that it needs. Now this is expected, and under normal operation the reactor control system will adjust the control rods to keep the reactor rate constant. In an active reactor, the Xenon-135 gets removed by being burned. When it absorbs a neutron, it becomes Xenon-136, which is much less likely to absorb a neutron and is very stable. Or if the reactor is idle, then it's not generating any neutrons, so this will decay into cesium-135 with a half-life of something like 9.5 hours. But it's important to realize that if the reactor power is reduced, the xenon production will continue at the rate from 6.5 hours ago. But the burn rate now occurs at the lower power levels, so bringing a reactor power down puts it in a situation where the neutron poison builds up and slows things down even more. Normally the reactor was designed to operate at about 3200 megawatts, but for most of the day preceding the accident it had been running at about 1600 megawatts. For the test, the power was supposed to be brought down to about 700 megawatts. And to be clear, when I talk about reactor powers here, this is the thermal power being generated inside the reactor. This is not the electrical power that is coming out of it. So the power reduction from 1600 megawatts to 700 began at about 10 minutes past 11. And just over an hour later, the operators who had just changed shifts managed to stall the reactor and the power levels plummeted down to about 30 megawatts, too low to run the test. At this point, the reactor was in a state where it was going to be really hard to bring it back up to power. That Xenon 135 was still building up and it wasn't being burned off because there weren't enough neutrons flying around. Any neutrons that were being generated was being used to burn up the Xenon. This is colloquially referred to as being stuck in the Xenon pit. But that wasn't the only effect choking the reactor of its neutrons. Remember that water is a weak neutron absorber. Now during normal operation, the cooling water is being boiled and that creates low density voids in the water. And this reduces the effective density of the water and therefore the amount of neutron absorption. So when the reactor power crashed all the way down, the water wasn't being boiled and that means it was absorbing even more neutrons than normal. So, under pressure from the lead engineer, the controllers attempted to restore the reactor to a power level where the test could occur, which meant they had to reduce the neutron absorption, and of course, they did this by pulling control rods further and further out of the core. The control rods in the RBMK reactors used boron carbide as their neutron absorber. But if they were simply pulled out of the core, then the space left behind would contain water, and that is also a neutron absorber. So to enhance the effectiveness of the rod, they would instead pull in a piece of graphite that would act as a moderator and therefore enhance the reactivity of the system. Therefore, this in theory made the control rods much more powerful controls of the reactor. Normally there were more than 200 rods used to control the core, but with all the Xenons stealing their neutrons, the operators pulled almost all of them out. There were equivalent of less than 8 rods left actively controlling the core. And yes, that does sound dangerous, but I imagine that the operators were no doubt comforted and encouraged to do this to push the limits because they knew that if things got out of hand, there was always the emergency power shutdown switch that could reinsert all of the control rods as quickly as possible. By manually pulling so many rods out of the core, they were able to get the reactor back up to power of about 200 megawatts, well below the power that they should have had according to the test protocol, but high enough that by manually managing the water flow through the reactor, they were generating enough steam to spin the turbines up to their operating speed. And so the test began. The turbines were isolated and they began to spin down. And it was at this point things went wrong in a big way. With so many of the control rods removed, the water had become a significant contributor to the neutron absorption. And with the power level so low and the cooling system running at a correspondingly low speed for the power, the reactor becomes very, very sensitive to the boiling of the water. As the water begins to boil and generate voids, fewer neutrons get absorbed, which in turn means that the reaction accelerates and heats the water even more. This positive feedback mechanism is summed up in the phrase positive void coefficient, and this term comes up regularly when describing the accident at Chernobyl. In reactors where water is a coolant and a moderator, then an increase in voids reduces the moderating effect and therefore slows the reactor. This is what's called a negative void coefficient, and it tends to make the reactor more stable. But the void coefficient is just one of several reactivity coefficients that describe how the reactor core responds to changes in reactor conditions. Another really good example is the fuel temperature coefficient, which tells us how the reactor reactivity changes as the fuel heats up. This is usually negative too, so that as the reaction gets going, it acts to slow things down. A really good example of this fuel temperature coefficient is the TRIGA reactors, which are research reactors that supposedly could be operated by high school students. These have extremely negative fuel temperature coefficients. They generate large, short-lived pulses of power that are very quickly arrested as the fuel heats up. The mechanism behind this is actually pretty complicated, but roughly speaking, as the fuel heats up, the atoms in the solid vibrate more, and this motion has to be added to the neutron speed, changing the effective velocity of your neutrons flying through the core, which in turn affects the absorption and scattering parameters. And so the fission cross-section effectively drops off. And it's sometimes called the Doppler coefficient because it's a result of Doppler shift of the neutrons encountering the atoms. But look, the point here that I'm making is that reactors are designed to operate in regimes where all these coefficients, all these factors result in a self-stabilizing reaction. And in the RBMK reactors, the destabilizing positive void coefficient of the water was normally offset by this and other stabilizing mechanisms. With the reactor in this low power, low flow state, some changes in the pressure, flow, or temperature began a power feedback loop, and the reactor power began to rise rapidly. And as the power began to rise, the water began boiling at lower and lower points in the channels, allowing the reaction to effectively move down in the core. See, normally at higher water flow rates, if this happened, the pressure of the water would push the voids back up and it would self-stabilize. But with the water flow being low because of the low power, that contributed to reactor instability. Around this time, the reactor scram control was triggered. This was the AZ5 switch, or the EPS, Emergency Protection System 5 control. This is actually a cluster of 6 buttons with plastic covers and wax seals so that you couldn't casually trigger them. Each of the buttons initiated different safety procedures. For example, I think one would bring it down to 50% slowly, and there would one that would bring it down to 50% quickly, but AZ5 quenched the power to zero as quickly as possible. And of course, the way it quenched the power to zero was by inserting those control rods as quickly as possible. Unfortunately, this wasn't a particularly fast process because the rods had to push down these channels and push the water out of the way. And they would only move at about 40 centimeters per second. The core was about 7 meters long, so it would take 18 seconds to completely push the rod down through the core. The control rods also had to push the graphite rods that had taken their place out of the way. Now, those reaction-enhancing rods were about 4.5 meters long, and they were positioned so that they were central to the core. That meant that you had about 1.25 meters of water above and below them. This had the effect that when they were being pushed through the core, the lower couple of meters initially had water displaced and replaced by graphite. And that meant the reaction at the very bottom of the core was enhanced as soon as you started shutting the reactor down. So in an effort to get power for the test, the controllers had pushed the reactor into a configuration where they had started getting the power, but it was no longer stable. And when that power started to come in, they tried to shut it down, but the process of shutting it down actually temporarily enhanced the reaction for a few seconds. And in those few seconds, the power skyrocketed. It shot up way beyond the design limit. And that's what happened. Seconds after the scram started, there was an explosion, followed a few seconds later by an even larger explosion which blew the top off the reactor and left it sitting at an angle. The final power reading that was recorded in the control system was 33 gigawatts, about 10 times higher than the design power of the station, but most models of this excursion suggest that it may have peaked at over 300 gigawatts. The actual mechanics of the explosion are still somewhat open to debate. Most people believe that the increase in power flash boiled the water to steam in the channels and then caused the pipes to rupture. And the second larger explosion may have been due to water being disassociated into hydrogen and oxygen by the heat and then subsequently collecting and combusting elsewhere. But there are those that argue that this was literally a small nuclear explosion where the reaction went prompt critical and ran away so quickly that it only stopped when the fuel was vaporized and exploded beyond the point of criticality. In one scenario, the vaporized material literally shoots out of the channel like a jet of plasma directed skywards. Regardless, once the power ran away, there were many mechanisms that could have led to the destruction of the reactor and its containment. It was important to realize that at the time, most experts in the world thought the idea of a nuclear reactor having a runaway excursion and explosion like this was impossible. And of course, the reason this was so far-fetched was because reactors are designed to prevent these circumstances, and even the shortcomings of the RBMK reactor were remedied in later years. There are still a number of RBMK reactors operating around the world, even although Chernobyl's reactors 1 through 3 were only shut down a few years ago. But that's my cold analytical physics side of things. The events that happen after the explosion are where the real meat of the drama lives, and the TV show does do a fabulous job of putting the viewers into some of these situations. And yes, there are some horrific scenes of victims suffering from extreme radiation poisoning, and that's the reality some of the first responders had to experience. But having seen that, it's important that you keep in mind that scientific study of energy generation and the human cost of energy generation shows that nuclear is actually one of the safest options out there. So I don't want you to come away from this video thinking that all nuclear reactors are a potential Chernobyl waiting to happen. That's simply not the case. But I do hope you come away from this with a bit more understanding of the physics and perhaps a bit more respect for power in general. I'm Scott Manley. Fly safe.